All right, since all this problem is asking us for is basically I2, let's solve for I1 first. We can plug that in here in terms of I2, solve this equation for I2, and we'll be done with this problem. All right, so let's separate this to two different sides here. Basically just say this is equal to this whole thing right here. And basically just want to solve for I1. So what we should probably do is get this into, let's get this into a better form here. Let's just do some math. J 18.85 minus 15.9. I get 2.93. So it's going to be 20 plus J 2.93. And then that whole thing is going to get divided by J 3.14. And that's going to give us our value for I1. All right. So let's throw that into my calculator. 20 plus basically my, divide by 3.14 times J. And I get that I1 is equal to I2 times 0.934 minus J 6.37. Okay? So now I can take this and plug it back into equation 1. So let's bring, let's slide this over a little bit and create some space. So for plugging into equation 1, it's going to be 10 minus this expression. Actually, let's just copy and paste it. I've gotten so used to writing on the iPad now that it's hard for me to do anything on real paper, which is bad. Okay, so this, and then that's me plugging I2 in for I1 right here. So now I still need to multiply that by that entire impedance here. So let me grab that impedance. Okay, throw that in right here. And then plus I2 times J 3.14, sorry. And then that whole thing is equal to 0. So let's basically rewrite this thing. But I'm going to multiply these two terms together, right? They're going to get multiplied together. So let me throw that into my calculator. 5 minus 15.9 times I. And that's plus I times 6.28. Okay, yeah, that makes sense. And then I multiply that whole thing by my 0.934 minus J 6.37. Okay. Interesting. I get 10 minus I2. Actually, these are all negatives, so it's really just written as I2 times 56.57 plus J 40.82, I guess you could say. And then there's a plus J 3.14, so let's just add that in there. So that's going to be 43.96 instead. And then that's equal to 0. And so now I just need to say that I2 is equal to negative 10 divided by this term here. Just like that. And let's see what that comes out to. So let me add I'm going to have to multiply this by -1. Sorry, I'm doing a lot of calculator work here. And make sure I don't make any mistakes. So I multiply this by -1, then I add 3.14 times I. Okay, so now I have what I need, and then I do -10 divided by that thing, and that should give me I2. Okay, so I get -0.11 plus J 0.086. That's my I2. And so if I convert that into polar, I get that I2 is equal to 0.139 angle 142.15 degrees amps. I am going to scroll on the textbook and see if that is correct. I really hope that it is. IL equals 139.5 milliamps, angle 142. Wow, okay, that's awesome. That is correct. Okay, I don't know why I was feeling like that was going to be off. I think it's just these problems are so prone to algebra errors. But this is correct. If you want to check this example in the book, you can check that in chapter 11, page 606 of the Eulaby textbook. And of course, the final answer asked for IL. This is I2. It asked for IL of t. We can say that IL of t is I2 of t, and it's just going to be 0.139 times the cosine. Remember, it was a cosine of 2 pi times 1k times t plus 142.15 degrees. And that's got units of amps. Okay, so that is the final answer right there for this example problem. All right, so we're done with this example. Think that that's good. We got another example loaded up, so in the next video we will solve this next more complicated example, probably over the course of three or so videos again, but really just want to start hammering in some of these concepts through example. I think it's really helpful to solve example problems and for you to see the math and to see the dot convention used, etc. Okay, so I'll end this video here and we'll see you guys in the next one for another example.